In this video I will look at the sideband noise of this amplifier, an Avantek UTC-565-1, 10 MHz to 500 MHz. I have the data sheet from the internet, and what I can find here is, for example, that phase noise at 500 MHz and 1 kHz offset should be typically minus 165 dBc per hertz. Now I'm looking at it at 10 MHz, and we will see what I can find. Here is the output from the interferometer on the Linrad screen, and we can see immediately something is very not correct. These noise sideband humps have some cause, and when I click on one of them we see there are many carriers separated by 100 Hz approximately. I'm feeding the amplifier through this cable from this power supply, and I don't know what's inside, if it is a switch power or if it is an analog one, but that doesn't really matter. I will put a filter on the supply voltage. So I added an RC filter. R is this red cable, several of them that form a small resistance, and then this huge capacitor. What is it? 60,000 microfarads. This made a big difference. Those ugly sidebands are no more there, and I can look close to the carrier, and this looks normal. There are some sidebands due to the BNC connectors, but there seems to be nothing due to the DC voltage. So I calibrate and measure what are the levels. They are pretty high. With a coupler in one branch of the interferometer, I can pick up the main signal, the carrier, and I have calibrated the SDR IP, which I used to pick up that signal. So it should show 0 here, 0.00 something. And then I have this signal 100 kilohertz down, and it comes here at 9.9, and I put it in the center of the filter, and you can see here it comes at minus 89.4. I was a little bit careless. It comes as 80.02. If I click outside the yellow line here, I get undefined points. That could be 0. So that is something to be careful about when using this tool. So anyway, I have set it to minus 80 decibels, and I changed the frequency, 9.999 megahertz. That is up to a place very close to the signal. So it's here, and then I check what is the level now. Minus 79.87. So I increased the level by 0.1 dB, like that, and then it's close enough to minus 80 over the entire frequency range that I'm interested in. Now the injected signal is at 9.9 megahertz, and I have calibrated the Linrad S-meter to show minus 80. And then I switch off that injected signal, And now I can read the noise floor in decibels below the carrier and in a bandwidth of 1 kilohertz. So I read minus 140.8 dBc per hertz. Sorry, dB in 1 kilohertz means 170.8 dBc per hertz. And now I introduce a lot of attenuation here, and that reduces the signal into the low noise amplifier after the second hybrid, and the noise here is now much lower, so I don't have to worry about contribution from the amplifiers. So the measured value is really from the amplifier under test. I have now moved the injected signal to 10 kilohertz offset, and the level I see there is different by 0.7 dB. That's because of the amplifiers after the interferometer and in front of the perisys. They have some selectivity and are not perfectly flat. So I have to change the calibration to make it show minus 80. Like this. 79.998. And then I switch off the generator here. And again, here is the noise floor, this time at the 10 kilohertz offset. And I read minus 140.7, means minus 170.7 dBc per hertz. Not very different from what I saw before. Now the separation is 1 kilohertz. And I check the level, and it's still very close to minus 80. I only moved 9 kilohertz from the previous frequency, so the gain through the amplifiers is very nearly the same. I have changed the bandwidth from 1 kilohertz to 100 hertz, and then I switch off the injected signal. And here comes the noise at 1 kilohertz. Minus 150.1 means minus 170.1 at 1 kilohertz. The bandwidth is now 10 hertz and the separation 180 hertz. And I have to have this narrow bandwidth to avoid the spurs. The spurs come from the BNC connectors because they are gold on nickel, and nickel is ferromagnetic. You can see about that in a previous video. The noise here is minus 156.1. I can check once again. Minus 156.2. And this is 70 hertz away, and the bandwidth is still 10 hertz. And then here I see minus 154, means minus 164.7 dBc per hertz. And this will be enough for this unit. We can see the noise becomes much stronger, much closer, but it isn't really so interesting. Well, one more data point. This is 20 hertz separation, and here the noise is minus 150.1, means minus 160.1 at 20 hertz separation. I'm now running one instance of Linrod in coherent 2 mode here. I have set a fairly narrow filter, and this is the carrier of the main oscillator, and I have unbalanced it a little to have a fairly strong carrier. And it is unbalanced in amplitude, not phase. So the phase is correct for the detection of in-phase and out-of-phase signals. And then I have a second instance of lean rod here, running on the signal emitted. And I find that at large separations, wherever I click, I see that the green and the red tracks are at the same level, means phase noise and AM noise are at the same level. But when I click very close, then I can see that the green track is stronger than the red, means AM noise is dominating. I can expand a little bit. And the noise close to the carrier here is dominated by AM noise, and the spurs are to a large extent also AM, although here is a spur that has an FM component that is fairly strong. So I'm not surprised by this. This is a bipolar amplifier, and it is likely to give AM noise more than FM noise, I think. And I don't know whether a better stabilization of the current through the device could improve this, but this is the result I have, and I think it is consistent with manufacturer specification, because this carrier comes at 48 on the scale, because the sampling rate is for 96 kilohertz, so the center is at 48, and 1 kilohertz away, that is here, and 1 kilohertz away, AM noise is very close. It's maybe, I can try to read it out. No, it's too close to the edge here still. And I have to wait, but you can see the difference looks like about 1 dB. So at 1 kilohertz frequency separation, I observe minus 170, and that is AM plus phase noise. And the phase noise is a little bit weaker, so the phase noise at 1 kilohertz is something like minus 174. And the manufacturer doesn't specify at this kind of a low frequency, but that is what I have found. And after waiting long enough, I find that the difference is 1.1 dB, in that the AM is stronger by 1.1 dB than the FM or the phase noise. To balance the interferometer, I have had to insert 22 decibels of attenuation. So the input signal here is 22 dB below the level I get from this oscillator, and it is attenuated by 1 dB. So I can see what happens if I reduce by 10 dB here. Then the balance changes a little bit. And I have to wait for the noise level. It didn't change. But when I look at close range, it did change. It means what I see at wide separations is the white noise floor associated with the noise figure of this amplifier. So at close range I have sideband noise, means the amplifier is modulating, but that's only at very narrow range. So I have minus 170.8 at 100 kilohertz and very close at 10 kilohertz. Let's say this is just a measurement error, so I say 170.7 for the distant noise floor. Means the oscillator power is plus 27 dBm, because the oscillator is plus 30 and then there is a hybrid splitting it into equal parts. Then there was 1 dB of attenuation in front of the interferometer and 22 dB more in front of the device under test. Means the unit is seeing plus 4 dBm at its input connector. So with minus 170.7 dBc per hertz, it means minus 166.7 dBm per hertz with a 4 dBm signal. From that I can compute the noise figure, which comes out as 7.3 dB. So looking at the data sheet, they say noise figure typical 8 dB. And 7.3 seems to be in the right ballpark then.